We've spent decades asking one terrifying question. What if aliens come to Earth? The far more disturbing question is this: what if they can't? No matter how intelligent they become or how long they survive. In this video, you'll uncover the hidden reason every alien civilization may be forever locked away from us, and why that changes everything we believe about our place in the universe. Get ready. Let's begin. Do you know the actual distance to the brightest star in the night sky? Step out into the Mojave Desert on a clear night, far from any city, far from any artificial glow. Stand still and look up. What you see is staggering. Thousands of stars spread across the sky like a flat carpet pressed against the darkness directly overhead. They appear close. They appear arranged. They appear almost without exception, as though they belong to the same ceiling. That feeling is not wonder. That feeling is a lie. The human brain did not evolve to measure interstellar distances. It evolved to judge the gap between a hunter and its prey, the width of a river, the distance to the tree line at the edge of a field. For hundreds of thousands of years, the furthest thing a human mind ever needed to accurately measure was a few miles away, perhaps a few dozen on a clear day from a high ridge. That is the instrument you are using when you look at the night sky, a ruler calibrated for footpaths, being asked to measure the cosmos. When your eyes take in the night sky, your brain does something automatic and almost completely invisible. It collapses three-dimensional space into a two-dimensional dome. Stars at vastly different depths get projected onto the same curved surface in your visual field, the way a map flattens a sphere. The result is that every star appears to exist at roughly the same distance from you, like light fixtures hanging from a ceiling at the same height. Your brain processes them as neighbors. They are not. Consider Sirius. It is the brightest star visible in the night sky, the one that dominates winter evenings in the northern hemisphere, burning with a sharp blue-white intensity that makes it unmistakable. It looks close. It looks brilliant and immediate. The light hitting your eyes right now left Sirius approximately 8.6 light years ago. That translates to roughly 50 trillion miles. The photons you are registering tonight departed that star around the year 2016, before a single one of the events defining this decade had taken place. Now shift your gaze to Betelgeuse, the red giant marking the left shoulder of Orion. It glows with an amber warmth and sits comfortably within what most people would call the neighborhood of the winter sky. The light you see from Betelgeuse tonight left that star approximately 700 years ago. That light was already traveling through space when Europe was being devastated by the Black Death in the 14th century, when roughly 1/3 of the continent's population was dying of bubonic plague. The star you are looking at is not a neighbor. It is a message from the medieval world, still arriving. This illusion is not merely poetic. It is structurally dangerous to every casual assumption ever made about extraterrestrial visitors. When someone imagines an alien civilization capable of reaching Earth, the first mental image almost always involves a journey across a sky that looks manageable, a sky that the human visual system has already preprocessed as finite and traversable. The night sky makes the stars look like destinations. That misperception is the foundation on which an enormous amount of wishful thinking has been quietly constructed. Pull the scale back further. Alpha Centauri, the nearest star system to our own sun, sits 4.24 light-years away. That number sounds modest until you convert it honestly. If you compressed the distance between Earth and Alpha Centauri down to a single inch, the Moon would be just 1/400th of an inch from Earth. The nearest stellar neighbor, reduced to 1 inch, still makes the Earth-Moon distance nearly invisible. That is not closeness. That is a different category of separation entirely. NASA's New Horizons spacecraft holds a meaningful distinction. Launched in 2006, it is the fastest human-made object ever to depart the solar system, currently traveling at approximately 36,000 miles per hour relative to the sun. That speed is not modest. It is a velocity that would carry you from New York to Los Angeles in about 5 minutes. And at that speed, traveling continuously without pause or deceleration, New Horizons would require approximately 78,000 years to reach Alpha Centauri. 78,000 years. The entirety of recorded human civilization fits inside a fraction of that number. Every empire, every language, every religion, every scientific revolution humanity has ever produced fits inside a sliver of the travel time needed to reach the single closest star, using the fastest machine we have ever built. The night sky is the most beautiful deception in the history of human perception, and that deception matters. Because every conversation about alien visitors begins here, with eyes that cannot help but lie about the scale of the universe they are trying to comprehend. But this is only the nearest star. What happens when we look at the rest of the galaxy and realize that distance is only the first layer of a problem that goes much, much deeper? If the Milky Way were the size of the continental United States, where do you think our solar system would be located? Alpha Centauri is 4.24 light-years away. That sentence, read aloud, takes about 2 seconds. The number itself sounds almost manageable. 4.24. You could say it between sips of coffee, but the moment you try to hold the actual physical reality of that distance in your mind, something quietly breaks down. The brain reaches for a frame of reference, finds nothing adequate, and substitutes a feeling of vague largeness that bears no resemblance to the truth. Now scale outward from that single number to the full structure of the galaxy, and the breakdown becomes total. The Milky Way stretches approximately 100,000 light-years from edge to edge. It contains somewhere between 200 billion and 400 billion stars, depending on how the counting is done and which estimates are applied to the dimmer, harder to detect populations. Our solar system does not sit anywhere near the center of this structure. It lies approximately 26,000 light-years from the galactic core, tucked inside a relatively minor spiral feature called the Orion Arm, positioned roughly 2/3 of the way out from the center toward the outer edge. We are not in the heart of the galaxy. We are in the suburbs, on a quiet spur, orbiting an unremarkable star. To make any of this feel real, the mind needs a model it can actually picture. So compress the entire Milky Way down to the size of the continental United States. In this model, every single star becomes a grain of fine sand, barely visible to the naked eye. At this scale, our solar system and Alpha Centauri are 2 grains of sand sitting approximately 4 inches apart, somewhere in the middle of Nevada. 4 inches. That sounds almost intimate. But a civilization located 1,000 light-years from Earth, in this same model, is sitting in a completely different state. Not a different county, not a different region, a different state entirely. And a civilization located 5,000 light-years away is somewhere near the opposite coast. The full diameter of the galaxy, 100,000 light-years, stretches from the Atlantic seaboard to the Pacific. The galaxy looks dense and crowded on a poster. In this model, you begin to feel what it actually is, an enormous expanse of emptiness, punctuated by occasional grains of sand, separated by distances that dwarf anything human experience has ever calibrated against. The average distance between neighboring stars across the Milky Way runs between 4 and 5 light-years. That spacing means most of the galaxy, by volume, contains absolutely nothing. No stars, no planets, no warmth, just cold vacuum extending in every direction for distances that take years of light-speed travel to cross. The galaxy is not a crowded room. It is a room the size of a continent, with a few thousand grains of sand scattered across the floor, and vast stretches of empty floor between every grain. In 2022, the European Space Agency's Gaia Space Telescope released its 3rd major data catalog, mapping the precise positions and motions of nearly 1.5 billion stars across the Milky Way. 1.5 billion individual stellar objects measured with extraordinary precision, and that catalog still represents only a fraction of the galaxy's total stellar population. What Gaia confirmed, with a level of detail never previously achieved, is a distribution so sparse and so vast that the emptiness between stars is not an occasional gap. It is the dominant feature of the galaxy. There is one more model worth sitting with. Place a basketball in the middle of New York City and call it the sun. At that scale, Earth becomes a small bead roughly 94 feet away. The moon sits just 3 inches from that bead. Mars, at its closest approach, is about a block and a half away. Neptune, the outermost planet, is roughly a mile out. And Alpha Centauri, the nearest star, is a similar basketball sitting somewhere near Portland, Oregon, 2,700 miles away. 2,700 miles to the nearest neighbor, and everything between those two basketballs is empty. This is the geometry that makes two ideas completely incompatible. The idea that the galaxy may be filled with life, which serious scientists consider genuinely plausible, and the idea that alien civilizations are regularly making the trip to Earth, which the geometry of the galaxy makes functionally absurd. A galaxy full of life is not a galaxy full of visitors. The distance between those grains of sand is not a road. It is a wall. But suppose a civilization accepts that wall and decides to build a ship anyway. What will they encounter? The answer will make you realize that the universe is not just vast. It was built to resist. How much energy do you think it takes to push a car to 10% of the speed of light? Light travels at 670 million miles per hour. That number is not a speed record waiting to be broken. It is not an engineering benchmark set by the most advanced civilization in the universe. It is a structural property of space-time itself, woven into the geometry of reality at the most fundamental level. Every particle, every wave, every signal, every interaction in the cosmos obeys it without exception. It is not the fastest speed currently achievable. It is the fastest speed that can exist. To cross interstellar distances in any time frame that preserves the coherence of a civilization or a mission, a spacecraft must reach a velocity that at least begins to approach that limit. 10% of the speed of light is the number that serious physicists and propulsion theorists use as a minimum meaningful benchmark. At 10% of light speed, a craft travels at approximately 67 million miles per hour. The journey to Alpha Centauri at that velocity takes 42 years. Not comfortable, but within the range of a human lifetime. Drop the speed to 1% of light speed, and the same journey stretches to over 400 years. Well beyond any individual life, and deep into the territory of civilizational commitment. 10% is the floor, not the ceiling, for any interstellar mission worth launching. So what does it cost to get there? Take a spacecraft massing 1,000 kilograms. That is roughly the weight of a small car. No passengers, no life support systems, no radiation shielding, no navigation computers beyond the minimum, just a frame with instruments and a communication antenna. The simplest conceivable interstellar probe. Accelerating that object to 10% of light speed requires approximately 4.5 times 10 to the 17th joules of kinetic energy. That number needs an anchor to mean anything. According to the U.S. Energy Information Administration, the United States consumes approximately 4,000 terawatt-hours of electricity per year. 1 terawatt-hour equals 3.6 times 10 to the 15th joules. The total annual electrical consumption of the most energy-intensive economy on Earth comes to roughly 1.4 times 10 to the 19th joules. The energy needed to push that 1,000 kilogram probe to 10% of light speed represents approximately 40 days of the entire electrical output of the United States. Every power plant, every solar farm, every wind turbine, every generator in the country, running continuously for 40 days. Directed entirely at a single car-sized machine with no passengers and no way to stop at the other end. That last point deserves full attention. Acceleration is only half the energy budget. A probe screaming through the Alpha Centauri system at 10% of light speed crosses the entire system in a matter of hours and vanishes into the void beyond. To actually stop at the destination, the spacecraft must decelerate from 10% of light speed down to 0, which requires the same energy expenditure as the acceleration phase. The total energy bill doubles. 80 days of American electrical output? For a car-sized robot. One-way trip to one destination. The problem compounds the moment fuel enters the picture. In 1803, Russian engineer Konstantin Tsiolkovsky derived the equation that governs every rocket ever built. The relationship it describes is merciless. To go faster, a rocket must carry more fuel. But fuel has mass, and that additional mass requires still more fuel to accelerate it, which adds more mass, which demands more fuel in return. The feedback loop does not converge, it explodes. The best chemical rocket engines ever built, including the main engines of the space shuttle and the engines powering modern, heavy-lift vehicles, achieve an exhaust velocity of approximately 4.5 kilometers per second. Plug that figure into the Tsiolkovsky equation and ask how much fuel is needed to reach 10% of light speed. The ratio of fuel mass to payload mass required exceeds the total mass of the entire solar system by many orders of magnitude. This is not an approximation or a rough estimate. The mathematics is that unambiguous. Chemical propulsion cannot reach interstellar velocities, not with better engineering, not with larger rockets. The equation itself forbids it. Nuclear propulsion improves the numbers without changing the conclusion. Even the most ambitious nuclear pulse propulsion concepts studied during the mid-20th century, designs that involved detonating sequences of nuclear warheads behind a massive pusher plate, reached estimated top speeds of perhaps 3 to 5% of light speed under theoretical conditions. Closer, but still fundamentally insufficient, and requiring engineering on a scale that has never been seriously attempted. Here is the point that matters above all others. Every figure in this analysis, the energy requirements, the fuel ratios, the velocity calculations, is determined by physical constants, the mass of the spacecraft, the speed of light, the kinetic energy relationship between them. These constants do not negotiate. A civilization 10 million years older than humanity still operates inside the same equations. Their engines may be more efficient, their fuel sources may be more energy dense, but they cannot pay less than the universe charges for the trip. The price is set by physics, not by the sophistication of the engineer. But what if they abandoned chemical fuel entirely and reached for the most energy-dense substance the universe has ever produced, antimatter? Would the energy wall finally collapse? The answer will surprise you in a way that is not entirely comfortable. How much antimatter do you think the entire history of human particle physics has ever produced? Every fuel humanity has ever used operates on the same basic principle. A chemical reaction, a nuclear reaction, some process that releases a fraction of the energy locked inside matter. The key word is fraction. Burn coal and you convert roughly 1/1,000,000% of its mass into usable energy. Split uranium atoms through nuclear fission and the conversion efficiency climbs to approximately 0.1%. Fuse hydrogen into helium, the process that powers the sun, and you reach roughly 0.7%. Each step forward in energy density represents a genuine leap. And yet every one of these processes leaves the overwhelming majority of the fuel's mass energy completely untouched. Antimatter is categorically different. When a particle of matter meets its antimatter counterpart, both are annihilated completely. 100% of their combined mass converts directly into energy, exactly as Einstein's equation demands, not a fraction, not a percentage. Everything. The gap between antimatter annihilation and the next best option is not incremental. Compared to coal combustion, antimatter releases energy with an efficiency 100 trillion times greater. It is the theoretical ceiling of what physics permits. No reaction in the universe extracts more energy per kilogram of fuel. So this solves the problem. A civilization with access to antimatter fuel has effectively unlimited propulsion energy. The wall comes down. The stars become reachable. Except, that is precisely where reality becomes ruthless. According to data from CERN, the European Organization for Nuclear Research, the total quantity of antimatter produced by every particle accelerator ever operated on Earth, across every country, across the entire history of experimental physics, amounts to approximately 15 nanograms. 15 nanograms is 15 billionths of a gram. It is a quantity so small it would be invisible to the naked eye. It would not register on a kitchen scale. It would not register on most laboratory instruments. If you gathered every antiproton, every positron, every antihydrogen atom ever created by human technology and placed them together, the resulting speck would sit on the tip of a needle and vanish from sight. That 15 nanograms, if it could be brought together and annihilated completely with an equal mass of ordinary matter, would release approximately 1.3 kilojoules of energy. 1.3 kilojoules is enough to heat roughly 1 tablespoon of water to boiling. That is the total antimatter energy budget of the entire human civilization across all of recorded particle physics research. The production cost makes the supply problem look almost trivial by comparison. NASA scientists estimating antimatter production economics have placed the cost of manufacturing 1 gram at approximately $62.5 billion, combined with an electricity consumption equivalent to the total electrical output of the United States sustained over many decades. 1 gram, a mass you could balance on your fingertip. Now consider what an actual interstellar mission requires. A 1,000 kilogram probe, the same car-sized object from the previous calculation, accelerated to 10% of light speed using an ideal antimatter drive, would require approximately 500 kilograms of antimatter combined with 500 kilograms of ordinary matter. At current production costs and current energy inputs, manufacturing 500 kilograms of antimatter would demand the combined economic output of every nation on Earth sustained for millions of years. The number does not represent an engineering challenge. It represents a quantity so disconnected from physical possibility that placing any timeline on it becomes meaningless. Scale that to a crewed vessel, a spacecraft large enough to carry even a minimal crew of 10 people, with life support, radiation shielding, navigation systems, food production, waste recycling, and structural mass, would weigh at absolute minimum hundreds of thousands of kilograms. Realistic estimates for a functional interstellar craft range into the tens of millions of kilograms. The antimatter fuel requirements scale proportionally. The figures produced by that calculation exit the domain of meaningful discussion entirely. And production is not even the final obstacle. Storage is its own category of impossibility. Antimatter annihilates on contact with any ordinary matter, including air molecules, container walls, and every conventional material known to engineering. The only proven method for containing antimatter involves suspending it in magnetic traps within near-perfect vacuum. CERN's current systems can trap antihydrogen atoms for measured periods, but the quantities involved are microscopic, and the energy required to maintain the magnetic containment fields substantially exceeds the energy stored in the antimatter itself. Scaling magnetic containment to hold hundreds of kilograms of antimatter stably across decades of space travel has no theoretical pathway, let alone an engineering one. The universe does not grant discounts for ambition. It does not offer special terms to civilizations that have worked hard or waited long. The physics of antimatter production, storage, and utilization applies identically to every civilization in the cosmos. A species 10 million years more advanced than humanity still cannot manufacture 500 kilograms of antimatter without confronting the same fundamental thermodynamic accounting. So what if they abandoned fuel entirely and instead left the energy source at home, pushing the ship from a distance? That idea sounds like genius until you look at the numbers. If a ship carries no fuel at all, could it be pushed by a laser beam fired from Earth? The previous two parts established a problem with no clean exit. Chemical propulsion cannot generate the exhaust velocity needed for interstellar travel. Antimatter propulsion requires quantities of fuel that exceed the productive capacity of entire planetary civilizations by millions of years. Every approach that involves carrying fuel runs into the same merciless feedback loop. More speed demands more fuel. More fuel means more mass. More mass demands more fuel in return. The loop has no floor. So the most elegant response to that problem is to eliminate the fuel entirely. Leave the energy source at home. Push the spacecraft from behind using something that costs no mass at launch. In theory, photons carry momentum. A sufficiently powerful beam of light striking a sufficiently reflective surface will impart a small but real force. Scale that force up dramatically, and you have a propulsion system that bypasses the rocket equation completely. This is not a fringe idea. In April 2016, physicist Stephen Hawking and entrepreneur Yuri Milner stood together at a press event in New York and announced Breakthrough Starshot, a research initiative funded with an initial $100 million to investigate exactly this concept. The proposal was specific and serious. A ground-based array of lasers producing a combined output of 100 gigawatts would fire a concentrated beam at a sail made of an ultra-thin reflective material. 100 gigawatts is approximately equal to the entire electrical generating capacity of the United Kingdom. That entire national energy output focused into a coherent beam aimed at a single target. The theoretical result was striking. A probe massing approximately 1 gram, essentially a chip-scale sensor package attached to a lightweight sail, could be accelerated to 20% of the speed of light. At that velocity, the journey to Alpha Centauri would take roughly 20 years. After decades of mission concepts measured in tens of thousands of years, 20 years sounds almost reasonable. That is what the concept promises. What the physics delivers is something considerably more complicated. The first problem is focus. A laser beam does not remain perfectly collimated across interstellar distances. It diffracts, spreading outward as it travels. Maintaining a beam concentrated tightly enough to continue pushing a sail that is already moving away at a significant fraction of light speed requires optical precision that strains the boundary between engineering and fantasy. A pointing error of 1/billionth of a degree, sustained over the acceleration phase, would cause the beam to miss the sail entirely and dissipate into empty space. The engineering tolerances required to keep a 100 gigawatt laser array locked onto a sail the size of a bedsheet accelerating to relativistic velocity represent a challenge with no demonstrated precedent at any scale. The second problem is deceleration. A sail accelerated to 20% of light speed arrives at the Alpha Centauri system and passes completely through it in a matter of hours. There is no mechanism to slow down. The laser that provided acceleration is now 4.24 light-years behind the spacecraft, physically incapable of pulling it back. The probe takes a brief burst of data and disappears into the void beyond, carrying no ability to stop, orbit, or linger. To decelerate at the destination, a second laser array of equivalent power would need to already exist there, which presupposes that someone has already solved the problem of getting to Alpha Centauri first. The third problem is scale. 1 gram is not a probe in any meaningful scientific sense. It is a sensor chip, a spacecraft capable of carrying even a modest scientific instrument package, a camera, a spectrometer, a basic communication antenna, and the power source to run them would weigh at minimum 10 kilograms. Scaling the laser array to accelerate 10 kilograms to the same 20% of light speed requires tens of thousands of gigawatts of laser power. That figure exceeds the total electrical generating capacity of the entire planet Earth. The concept that works for a chip-scale sensor becomes globally impossible for anything approaching a functional probe. The fourth problem is the interstellar medium itself. At 20% of light speed, a dust grain measuring just 1 micrometer across, smaller than a human red blood cell, carries kinetic energy equivalent to a rifle bullet on impact. The sail proposed by Breakthrough Starshot is designed to be extraordinarily thin, measured in nanometers, to keep mass as low as possible. A material that thin encountering dust grain impacts at those velocities would not be damaged. it would be shredded within the first hours of flight. Long before the acceleration phase is even complete, the light sail is a genuinely beautiful idea in physical terms. It attacks the right problem from a creative direction, eliminating onboard fuel and sidestepping the rocket equation entirely. But in solving one constraint, it creates three others of equal severity: focus, deceleration, scale, and material survival do not yield to the same solution simultaneously. The energy wall cannot be broken with fuel. It cannot be broken with lasers. So what happens when a civilization abandons all of these approaches and asks instead, why move through space at all? Why not bend it? This is where science and science fiction finally meet and part ways in the most painful way possible. Did you know that a physicist once published a mathematically valid equation for a warp drive? Every propulsion method examined so far operates within the same fundamental constraint. You move through space. You cross the distance between origin and destination by physically traversing every mile that lies between them. The energy cost is set by that distance, that mass, and the speed of light. There is no negotiation. The most radical response to that constraint is to stop thinking about moving through space and start thinking about moving space itself. In 1994, Mexican physicist Miguel Alcubierre published a paper in the peer-reviewed journal Classical and Quantum Gravity that stopped the theoretical physics community in its tracks. Alcubierre had found a solution to Einstein's field equations of general relativity that described something genuinely extraordinary: a region of space-time configured so that space contracts in front of a vessel and expands behind it, creating a wave that carries the ship forward the way a surfer rides a swell. The vessel inside the bubble does not accelerate through local space at all. It sits still while the geometry of space-time around it does the moving. The elegance of this idea runs deep. Because the ship itself never exceeds the speed of light within its local region of space, the proposal does not technically violate special relativity. General relativity permits space-time itself to expand or contract at any rate. The universe's own expansion already carries distant galaxies away from us faster than light. Alcubierre was not proposing to break the rules. He was proposing to use them differently. The mathematics is internally consistent. This is not pseudoscience. It is a legitimate solution to a legitimate set of equations published in a legitimate scientific journal. For a brief period after publication, it was treated seriously as a theoretical possibility worth investigating. Then the physical requirements came into focus, and the elegance collapsed. Sustaining a warp bubble requires a substance with negative energy density. In practical terms, this means matter that weighs less than nothing. Matter that gravitationally repels rather than attracts. Matter whose energy contribution to a region of space is below the energy of pure vacuum. This category of material is called exotic matter. Small quantum effects related to the Casimir effect hint that negative energy densities may be achievable in extremely limited microscopic contexts. But exotic matter in the quantities and configurations required to sustain a macroscopic warp bubble has never been observed, never been produced, and has no established theoretical pathway to existence at any useful scale. Alcubierre's original calculations placed the energy requirement for creating and sustaining a warp bubble at approximately the mass energy equivalent of the planet Jupiter. That figure is so remote from any conceivable engineering reality that it effectively ends the conversation before it begins. In 2012, physicist Harold White at NASA's Johnson Space Center proposed a refined geometry for the warp bubble that reduced the exotic matter requirement dramatically, down to approximately 700 kilograms under optimized conditions. That revision received considerable attention in popular science media and was treated in many quarters as a meaningful step toward practicality. 700 kilograms sounds manageable compared to Jupiter. It is not manageable at all. 700 kilograms of a substance that has never been observed to exist in any stable, producible form at any scale remains an infinite distance from engineering reality. The revision changed the number. It did not change the nature of the obstacle. A research group at the University of Santiago de Compostela published findings in 2021 identifying a further problem that operates independently of the exotic matter requirement. A warp bubble moving through space would accumulate high-energy radiation and particles at its leading edge throughout the journey. The way a ship's bow accumulates water, when the bubble decelerates and releases this accumulated energy at the destination, the discharge would take the form of a highly energetic burst, capable of destroying everything in the immediate vicinity of the arrival point. A warp drive, if it functioned as described, would not deliver travelers to a destination. It would deliver a detonation. There is also the problem of control. Inside a functioning warp bubble, the occupants are completely causally isolated from the space outside. No signal, no force, no instruction can cross the boundary of the bubble from the interior. The crew cannot steer, they cannot adjust course. They cannot stop the bubble from the inside because any action they take is confined to the local space within the bubble, which has no physical connection to the space-time geometry being manipulated around it. A warp drive, even in pure theory, is a one-way envelope with no return address. Between 2012 and 2016, NASA's Advanced Propulsion Physics Laboratory, known as EagleWorks and based at Johnson Space Center, conducted a series of experiments searching for any measurable evidence of warped spacetime at small scales, an attempt to find even a foothold of experimental support for the underlying physics. The program produced no repeatable, independently verified results of significance. The search for laboratory-scale evidence of warp physics returned nothing that the broader scientific community accepted as confirmation. Warp drive is not a solution. It is a mathematical question waiting for physics to answer. And physics has so far remained silent. But there is another shortcut that serious physicists still discuss: a tunnel punched directly through space-time itself. The problem is, the only thing that could hold it open has never been proven to exist. If wormholes exist naturally, why haven't we detected a single one? The warp drive at least had the quality of novelty. It was a concept that emerged from creative engagement with general relativity, a genuinely new way of thinking about how space-time geometry might be exploited. Wormholes are older. They did not arrive as a proposed solution to the travel problem. They emerged directly from Einstein's own equations, uninvited, as a mathematical consequence that nobody initially knew what to do with. In 1915, Einstein published the field equations of general relativity, the framework that describes how mass and energy curve spacetime and how that curvature governs the motion of everything within it. 20 years later, in 1935, Einstein and his colleague Nathan Rosen were examining the mathematics of black holes when they discovered something unexpected in the geometry. The equations permitted a structure connecting two separate regions of spacetime through a kind of tunnel, a bridge between points that might otherwise be separated by enormous distances. This became known as the Einstein-Rosen bridge. The concept is straightforward in its appeal. If two mouths of a wormhole could be positioned at different locations in space, an object entering one mouth would emerge from the other, bypassing entirely the physical distance between them. 4.24 light-years to Alpha Centauri becomes a single step. 1,000 light-years becomes a doorway. Distance. The wall that has defined every previous part of this analysis ceases to exist as a constraint. It is easy to understand why this idea saturated science fiction. From the film Contact in 1997 to Interstellar in 2014, the wormhole became the standard cinematic mechanism for making the universe feel navigable. But mathematics and physical reality are two separate things. A solution existing within the equations does not guarantee that the solution exists within the universe. The central problem is stability. The Einstein-Rosen bridge that emerges from the original equations is not traversable. It opens and collapses faster than any object could pass through it. The time scale of that collapse is measured in Planck time, approximately 10 to the negative 43 seconds, a duration so incomprehensibly brief that it makes no sense in any human frame of reference. Nothing in the universe moves or reacts fast enough to transit a wormhole before it pinches shut, creating a traversable wormhole. One that stays open long enough for matter to pass through requires threading it with exotic matter, the same substance with negative energy density that the Alcubierre warp drive demands. Without that exotic matter holding the throat of the tunnel open against the gravitational tendency to collapse, the wormhole closes instantaneously. With it, the wormhole might remain stable, but the requirement leads directly back to the same impasse encountered in the previous discussion. Exotic matter in the required configuration has never been observed, never been produced, and has no confirmed pathway to existence. In 2020, Princeton physicist Juan Maldacena and colleague Alexei Millikan published a proposal for a traversable wormhole that sidesteps some of the exotic matter requirements by drawing on quantum mechanical effects rather than classical negative energy. The proposal attracted serious attention precisely because it represented a genuine theoretical advance. But the conclusion it reached was quietly devastating for interstellar travel. Even in Maldacena and Millikan's model, information traveling through the wormhole moves more slowly than light traveling around the outside of it through ordinary space. The shortcut is slower than the long way. A wormhole built on this model does not help a traveler reach a distant star any faster. It is a tunnel that delivers you after the light from your departure has already arrived. The causality problem operates on an entirely different level and may be the most fundamental objection of all. Special relativity establishes that simultaneity is relative. Two events that appear simultaneous to one observer appear sequential to another, depending on their relative motion. A wormhole permitting instantaneous travel between distant points, when combined with the relative simultaneity of special relativity, creates the mathematical possibility of arriving at a destination before you departed. This is not a quirky edge case. It is a direct consequence of the geometry, and it produces paradoxes that most physicists treat as strong evidence that traversable wormholes simply cannot exist in a universe governed by consistent causality. In 1992, Stephen Hawking formalized this intuition into what he called the chronology protection conjecture. The proposal states that the laws of physics will always conspire to prevent the formation of structures that allow travel backward in time. Specifically, quantum fluctuations near any wormhole that could be used for time travel would generate feedback loops of radiation that destroy the wormhole before it can be used. The conjecture has not been proven, but it reflects a broad consensus among theoretical physicists that the universe enforces a prohibition against causal paradoxes through mechanisms that may not yet be fully understood. Observational astronomy has provided no relief. The Event Horizon Telescope, the global array of radio observatories that produced the first direct image of a black hole's shadow when it captured the supermassive black hole M87 star in 2019 and Sagittarius A star at the center of the Milky Way in 2022, has delivered extraordinary confirmation of general relativity's predictions about extreme space-time curvature. What it has not found, in any of its data, in any survey of any region of the observable universe, is any observational signature consistent with a naturally occurring traversable wormhole. Warp drive requires matter that does not exist. Wormholes require matter that does not exist and violate causality. Space has no shortcuts. So suppose a civilization accepts all of this and decides to go any way slowly, directly, and patiently. What they will face is something more ruthless than distance and energy combined time, and time shows no mercy to anyone. How long did the longest-lasting civilization in human history actually endure? Every shortcut has now been examined and found wanting. Warp drives demand exotic matter that has never been observed. Wormholes demand the same and then compound the problem with causality violations. Laser sails cannot stop, cannot scale, and cannot survive the interstellar medium at the velocities they require. antimatter remains a laboratory curiosity measured in nanograms. The only remaining option is the one that was always there, sitting quietly beneath all the more elegant proposals. Go anyway, accept the distance, accept the energy cost, point the ship at the destination, and fly. So what does that actually look like in numbers that connect to something real? 1% of the speed of light is approximately 6.7 million miles per hour. That figure is not achievable with any current technology, but many physicists regard it as theoretically conceivable in the far future with sufficiently advanced fusion propulsion. It is the speed that serious interstellar mission planners use as a lower boundary for what a large crewed vessel might someday reach. Not optimistic, not pessimistic. A considered estimate for what advanced but physically plausible engineering might eventually deliver. At 1% of light speed, the journey to Alpha Centauri takes 424 years. That is already longer than the United States has existed as a nation. The United States, as of 2025, is 249 years old. A ship launched today at this speed would arrive at the nearest star when the American Republic, if it still existed in any recognizable form, would be approaching its 700th year, and Alpha Centauri is the closest possible destination. Scale outward to a star 1,000 light-years away. At 1% of light speed, the journey takes 100,000 years. That number needs to be placed against something concrete before it can mean anything. 100,000 years ago, anatomically modern humans were leaving Africa, spreading across a planet they shared with Neanderthals and Denisovans. They had no writing, no agriculture, no permanent settlements, no metal tools of any kind. The entire arc of everything humanity has ever built. Every city, every empire, every scientific institution, every piece of accumulated knowledge fits inside a fraction of that travel time. The whole of recorded human civilization, from the earliest Sumerian city-states to the present day, spans approximately 5,000 years. The Roman Empire, one of the most durable political structures in Western history, lasted roughly 500 years before fracturing beyond recovery. The United States, at 249 years, is already older than most republics in recorded history. 100,000 years is not a human timescale. It is not even a civilizational timescale. It is a geological one. No language spoken today will be recognizable in 1,000 years, let alone 100,000. No institution operating today has maintained continuous identity and purpose across even 5,000 years. The Code of Hammurabi, inscribed around 1754 BCE, is one of the oldest legal texts humanity has preserved. It survives because successive civilizations made deliberate choices to conserve and transmit it. Even so, the civilization that produced it vanished long ago. Nobody alive today is a citizen of ancient Babylon. Nobody carries forward Hammurabi's specific technical objectives. The text survived. The mission did not. An interstellar spacecraft launched toward a star 1,000 light-years away carries its programming in a language that will have no living speakers within a few centuries of departure. The institution that designed its navigation system will not exist when it completes 10% of its journey. The nation or civilization that funded the mission will be, in all likelihood, as remote and incomprehensible to its eventual descendants as Sumer is to us today. And consider what happens at arrival. The ship reaches its destination after 100,000 years of flight. It was launched by a civilization that is now dust. The beings who conceived the mission, debated it, funded it, and celebrated its departure have been gone for a span of time longer than all of recorded human history multiplied by 20. If the ship carries any message from its origin civilization, that message arrives as a relic from a world so remote in time that it might as well be archaeology. The ship is not a representative of its home civilization. It is a tombstone carrying instructions that no one alive remembers writing. This is the time wall. It does not care about the sophistication of the propulsion system. It does not respond to better engineering. It is simply the relationship between the distances involved and the timescales over which any organized civilization can maintain coherent purpose. And it stands equally high for every civilization in the galaxy, regardless of how advanced they are or how long they have survived. But what if they did not send a lone ship with a small crew? What if they sent a generation ship, a self-sustaining city in space, with thousands of people living and dying across the centuries of the journey? That idea sounds like it solves the time problem, but it opens a social hell that nobody really wants to think all the way through. How many people do you think are needed at minimum to maintain sufficient genetic diversity for a civilization? The generation ship concept has a surface elegance that makes it feel like a genuine solution. If no individual can survive the journey, send a community. Build a vessel large enough to sustain a self-reproducing population across centuries or millennia. The original crew lives, has children, ages, and dies aboard the ship. Their children do the same. Generation after generation carries the mission forward until the final cohort arrives at the destination. The problem of individual lifespan is bypassed entirely. The mission outlives any single person because the mission is carried by a population rather than a crew. The elegance survives only until you examine the actual requirements. In 2014, Cameron Smith of Portland State University published a detailed analysis of the minimum viable population for an interstellar generation ship. His findings, subsequently reinforced by multiple independent studies in population genetics, placed the minimum number at 10,000 individuals. 10,000 people are required to maintain sufficient genetic diversity across thousands of years of isolated reproduction, avoiding the inbreeding depression and genetic drift that would otherwise degrade the population's long-term viability and adaptability. Later analyses have suggested the number may need to be higher rather than lower. 10,000 people is not a crew. It is a small town, housing, feeding, providing medical care for, and psychologically sustaining 10,000 human beings in a sealed metal environment for 10,000 years requires a vessel of extraordinary size and complexity. The mass of such a ship pushes the energy requirements for acceleration back into the territory that the previous calculations already established as functionally impossible. The generation ship solution to the time problem reintroduces the energy problem at a scale that makes earlier figures look conservative. But set aside the energy for a moment and focus on what 10,000 people in a sealed container for 10,000 years actually means in practice. The most instructive real-world reference point is Biosphere 2, a sealed artificial ecosystem constructed in Oracle, Arizona. Between 1991 and 1993, 8 people lived inside a 3-acre enclosed structure designed to be a self-sustaining ecological system. The experiment was the most ambitious attempt in human history to create and maintain a closed biosphere. It lasted 2 years. Within that period, oxygen levels inside the structure dropped to levels that required external intervention to prevent serious health consequences. Crop yields failed to meet the population's nutritional needs. Pollinating insects died off, disrupting the agricultural systems that depended on them. The 8 participants divided into 2 factions that ceased meaningful communication with each other before the experiment ended. 8 people, 3 acres, 2 years, full support infrastructure from outside, and the system began collapsing within months. A generation ship would need to sustain 10,000 people in a sealed metal container with no external support, no resupply, no intervention, and no exit for 10,000 years. Every molecule of water must be recycled indefinitely without loss. Every calorie of food must be grown within the ship using artificial light and recycled nutrients. Every breath of oxygen must be biologically regenerated. Every gram of waste must be processed back into usable resources. No closed ecological system has ever been demonstrated to function at this level of completeness for more than a fraction of the time required. The sociological dimension is equally devastating. 500 years into the journey, 20 generations have been born and died aboard the ship. Nobody alive has any direct memory of the origin world. The planet that launched the mission exists only in records and oral tradition. After 2,000 years, the story of the departure has likely become mythologized, its specific technical details obscured by centuries of cultural drift and reinterpretation. After 5,000 years, the mission's original purpose may have been reframed so many times that it bears no meaningful resemblance to the intention of the founders. No human institution has maintained a single unchanged objective across 1,000 years. The major religious traditions that have persisted for millennia have all undergone transformations so profound that their founders would not recognize the institutions that claim descent from them. The notion that a community aboard a ship could maintain unwavering commitment to a specific technical mission for 10,000 years contradicts every observable pattern in human organizational history. There is also a question that philosophers have raised with increasing seriousness as the generation ship concept has received more attention. The people born aboard the ship did not choose to be there. They arrived into a mission conceived by ancestors they will never meet, committing them to a journey they cannot exit, toward a destination they cannot verify. For purposes they had no voice in defining. The ethical weight of that imposition is not trivial. A generation ship does not just carry people. It conscripts them across every generation of their lives into a project they never agreed to join. And at the destination, the people who step off the ship may not want to complete the original mission. They may not even know what it was. Suppose they solved all of it: the biology, the social structure, the psychology. The ship still has to survive, and the universe is not a gentle environment for fast-moving objects. What is waiting for it outside is not peaceful emptiness. It is a storm of bullets moving at cosmic speed. How much damage can a dust particle smaller than a human hair cause when it hits at 10% of the speed of light? The generation ship has been examined and found to be a catalog of compounding failures: biology, sociology, psychology, institutional memory. Each one alone presents obstacles that no civilization in human history has ever come close to solving at the required scale. Together they form a system of interlocking breakdowns that virtually guarantees mission failure long before arrival. But set all of that aside. Assume the population remains healthy, cohesive, and committed across 10,000 years of flight. There is still the small matter of the environment through which the ship is traveling. Most people, when they picture interstellar space, picture emptiness, total, featureless, absolute emptiness, a vacuum so pure that nothing exists between the stars. That picture is almost correct. Almost. The interstellar medium, the material that fills the space between stellar systems, is not a perfect vacuum. Measurements from decades of astronomical observation confirm an average density of approximately 1 hydrogen atom per cubic centimeter throughout much of the galaxy's disk, by any standard familiar to human experience. This is extraordinarily sparse. The air you are breathing right now contains approximately 27 quintillion molecules per cubic centimeter. The interstellar medium is roughly that many times less dense than the air in your lungs. In a laboratory on Earth, achieving a vacuum anywhere near this sparse would represent a significant technical accomplishment. But 1 atom per cubic centimeter, encountered by a spacecraft moving at 10% of the speed of light, is not nothing. At that velocity, each hydrogen atom the ship's hull meets carries a collision energy of approximately 1 mega-electron volt. 1 mega-electron volt places each individual impact in the range of ionizing radiation, the same energy regime associated with gamma rays and high-energy particle bombardment. No single collision at this energy level is catastrophic. What matters is the cumulative flux. Every square centimeter of the ship's forward-facing surface encounters billions of these atomic collisions every second. Not occasionally, every second. For years, for decades, for centuries. The effect is not an explosion. It is erosion, steady, relentless, atomic-level abrasion of every material on the leading face of the vessel. Over years and decades of continuous exposure, This flux displaces atoms from crystalline structures, degrades the molecular bonds holding materials together, and damages electronic components by progressively disrupting the semiconductor lattices that make them function. It is the physical equivalent of sandblasting the front of the ship at the atomic scale, without pause, for the entire duration of the voyage. Interstellar dust compounds the problem in a categorically different way. Individual dust grains in the interstellar medium average approximately 0.1 micrometers in diameter, smaller than the wavelength of visible light, invisible to any optical instrument. Their density in the galactic plane runs to roughly 1 grain per 10 to the 12th cubic meters. That sounds extraordinarily sparse, and by volume it is. But a spacecraft with a cross-sectional area of 100 square meters traveling at 10% of light speed toward Alpha Centauri over 4 years will encounter hundreds of such particles along its path. Each collision between one of these microscopic grains and the ship's hull at 10% of light speed releases energy equivalent to several kilograms of TNT. Not a scratch, not a dent, an explosive event concentrated at a single point on the hull, driven by kinetic energy that scales with the square of velocity. At 10% of light speed, the impact energy of a particle this small exceeds anything the known material science of structural engineering can absorb without penetration. Hundreds of these impacts over a 4-year journey to Alpha Centauri would perforate any known material repeatedly. For a journey measured in centuries or millennia, the cumulative damage calculation produces numbers that no plausible shielding architecture can address. Cosmic rays present a hazard that operates at an entirely different scale and cannot be shielded against by any means currently understood. These are protons and atomic nuclei accelerated to extreme velocities by supernovae, pulsar wind nebulae, and the active nuclei of distant galaxies. The most energetic cosmic rays ever detected carry energies up to 10 to the 20th electron volts, a figure so large it is difficult to contextualize. These particles pass through virtually any material. Meters of solid lead reduce the flux, but cannot stop it. The ship's hull, whatever it is made of, is transparent to the highest energy cosmic ray particles. Astronauts aboard the International Space Station, operating within low Earth orbit, and therefore still partially protected by the planet's magnetosphere, receive radiation doses approximately 10 times higher than people on the ground. Remove that magnetospheric protection entirely, as any interstellar spacecraft must, and the baseline cosmic ray exposure increases substantially. Extend the mission duration to centuries or millennia, and the cumulative biological damage to any crew accumulates without ceiling. The only engineering response to dust and particle impacts is to add shielding mass to the front of the vessel. Denser material absorbs more of the kinetic energy from incoming particles, but every kilogram of shielding added to the ship's mass must be accelerated along with everything else, feeding directly back into the propulsion equation. More shielding means more mass. More mass means more fuel. More fuel means more mass. The loop that was established in Part 3 has no exit here either. Dust grain impacts can be calculated, predicted, and designed against to some degree. But there is something that cannot be predicted, cannot be planned, for something that even the best built ship cannot prepare for: the complete and permanent loss of all contact with home. If you sent a message to a spacecraft 50 light years away, when would you receive the reply? The interstellar medium poses physical threats that engineering can at least attempt to quantify and partially mitigate. Add enough shielding, and you reduce the dust grain damage to survivable levels, even if the mass penalty is severe. Design the electronics with sufficient redundancy, and the cosmic ray degradation can be slowed. These are hard problems, but they are problems with a shape. What comes next has no shape at all. It is not a problem to be engineered around. It is a property of the universe that applies uniformly to every signal, every message, every piece of information that any civilization has ever tried to transmit across interstellar distances. The speed of light is not only the speed limit for physical travel, it is the speed limit for information. No signal of any kind, no radio wave, no laser pulse, No quantum entanglement effect usable for communication. Moves faster than light. There are no exceptions. There are no loopholes. There are no physical phenomena that carry information at superluminal speeds. This is not a provisional finding awaiting revision. It is one of the most thoroughly tested conclusions in the history of experimental physics. The practical consequence for an interstellar mission is immediate and total. Consider a specific scenario. A spacecraft is 50 light years from its home civilization. Engineers back home examining archived design documents discover a critical flaw in the ship's atmospheric filtration system, one that will cause carbon dioxide levels to rise to dangerous concentrations within decades if not corrected. They transmit a warning and detailed repair instructions the moment the flaw is identified. That transmission, traveling at the speed of light, takes 50 years to reach the ship. The crew receives the warning 50 years after it was sent. Their reply, explaining what tools and materials they have available for repairs, takes another 50 years to return. The engineers who identified the original flaw receive that reply 100 years after they sent the initial warning. Most of them are dead. The institutional knowledge required to devise a workable solution may have transferred to a new generation of engineers unfamiliar with that ship's specific configuration. That is the communication reality at 50 light years. At 1,000 light years, a single exchange of information requires 2,000 years from transmission to reply. For current reference, NASA's communication delay with New Horizons, now operating at the outer edge of the solar system, stands at approximately 22.5 hours as of 2024. That 22.5-hour delay already creates meaningful operational constraints for mission controllers. For an interstellar mission, the equivalent figure is measured in decades at minimum and centuries at most. The moment a spacecraft departs the solar system and begins its interstellar journey, it is operationally alone. There are no software updates that arrive in time to matter. There is no technical consultation that closes the gap between a problem's emergence and a solution's application. There is no news from the civilization that launched the ship. There is no confirmation that the civilization still exists. The ship and everyone aboard it are, from the perspective of any meaningful support relationship, permanently severed from everything that built them. This is not solely an engineering problem. The Hawaii Space Exploration Analog and Simulation Program, known as HISEAS, conducted a series of long-duration Mars mission simulations at a facility on the slopes of Mauna Loa in Hawaii. Crews lived in isolation for periods of up to 8 months, with all communication to the outside world subject to a 20-minute delay in each direction to simulate the signal lag of a Mars mission. The psychological effects of even that modest communication delay were measurable and significant. Crew cohesion, individual mental health, and decision-making quality all showed degradation patterns that researchers documented carefully. 20 minutes of delay, not 50 years, not 2,000 years. Human beings are social organisms shaped by millions of years of evolution within connected communities. The psychological architecture that underlies human cognition was built for a world where help could be summoned, where shared knowledge could be accessed, where belonging to a larger group provided the grounding that individual existence requires. Strip all of that away permanently, with no endpoint in sight, and the psychological consequences operate at a depth that no training program, no selection process, and no onboard support system has ever been demonstrated to prevent over long timescales. There is also the dimension that might be called the continuous obsolescence postulate. When a ship launched with the best available technology of its era arrives at its destination after 10,000 years of travel, every system it carries is 10,000 years out of date relative to the civilization that built it. Assuming that civilization still exists in any form, the ship arrives as an artifact of a vanished technological era, carrying instruments and capabilities that its origin civilization abandoned millennia ago. Whatever discoveries it makes, whatever data it collects, it reports them using methods that may no longer be readable by anyone who receives the transmission. And even if the ship survives all of this, the distance, the energy cost, the passage of time, the radiation bombardment, the complete isolation they still have to find Earth, and from 1,000 light years away, Earth is almost completely invisible. How far have our radio signals actually traveled across the galaxy so far? The ship has survived the interstellar medium. The population aboard has maintained cohesion across centuries. The systems have held together against the relentless atomic erosion of the void. Every barrier examined so far has somehow been overcome. Now the vessel is approaching its destination. It is moving through a region of the galaxy it was aimed at from the beginning. And here, at the final stage of a journey lasting thousands of years, it faces a problem that was present from the very first moment the mission was conceived, but never fully confronted. It has to find Earth from a distance of 1,000 light years. The Sun is one ordinary yellow dwarf star among 400 billion stars in the Milky Way. It does not pulse with unusual patterns. It does not emit radiation at anomalous frequencies. It carries no distinguishing marker that separates it from the millions of other G-type stars scattered across the galaxy's disk. From that distance, even with the most powerful telescopes, a spacefaring civilization could construct. The Sun is simply one unremarkable point of light in a field crowded with unremarkable points of light. Resolving Earth directly from 1,000 light years away is not merely difficult. It is beyond the reach of any telescope architecture that physics permits at practical scales. The James Webb Space Telescope, the most powerful space observatory ever launched, operates with a primary mirror 6.5 meters in diameter. Under ideal conditions, it can detect atmospheric signatures from planets orbiting stars a few hundred light years away, provided those planets transit their stars at the right angle relative to our line of sight. Detecting and characterizing an Earth-sized planet at 1,000 light years requires a telescope aperture measured in hundreds of kilometers. Not a larger version of Webb, a structure fundamentally different in scale from anything humanity has ever attempted or seriously proposed. Humanity's most detectable signature from a distance is its radio emissions. The first powerful, intentional radio broadcasts began in the 1920s. Those signals have been expanding outward at the speed of light ever since. As of 2025, our radio bubble has a radius of approximately 100 light years, encompassing perhaps a few 100,000 of the roughly 400 billion stars in the Milky Way. 100 light years against a galactic radius of 50,000 light years represents less than 0.2% of the distance from the Sun to the outer edge of the galaxy. The overwhelming majority of the Milky Way has received no electromagnetic evidence that Earth exists. A civilization 1,000 light years away has received nothing from us. Our signals will not reach them for another 900 years. And when they finally arrive, they will carry a message about a civilization that existed 900 years before the signal was sent, not the civilization of today. The signal strength problem compounds the invisibility. Radio waves obey the inverse square law without exception. Signal intensity falls in proportion to the square of the distance traveled. At 100 light years, the strongest television and radar transmissions Earth has ever produced have weakened to a level approximately 10 billion times fainter than the natural radio noise emitted by the Sun itself. Against the background electromagnetic cacophony of a star, our signals are not merely quiet. They are buried so deeply beneath the noise floor that distinguishing them would require a receiver of impossible sensitivity, pointed with extraordinary precision at exactly the right star at exactly the right frequency. There is a temporal dimension to this invisibility that adds another layer of impossibility. Even if a civilization 1,000 light years away somehow received our radio signals, the light they see from Earth tonight left our planet around the year 1025. They are observing medieval Earth. No cities visible from space. No industrial atmospheric signatures. No electromagnetic spectrum evidence of technology. A small blue world with an oxygen-rich atmosphere and no other obvious distinguishing features. one of potentially thousands of similar candidates scattered across the portion of the galaxy their telescopes can examine. Earth does not advertise itself. It orbits an average star in an average location within an average spiral galaxy, producing electromagnetic noise that barely reaches its immediate stellar neighborhood before fading below detectability. We are not a beacon. We are a whisper. And even that whisper has only traveled a tiny fraction of the distance to our nearest plausible neighbors. A civilization targeting Earth without prior knowledge of its location would be committing an extraordinary journey to find a world they cannot see, cannot detect, and cannot confirm exists. They would be traveling blindly toward a coordinate in space that contains, as far as their instruments can determine, one unremarkable star among hundreds of billions. If you cannot be found, no one comes. But suppose a civilization advanced enough to solve all of this distance, energy, time, radiation, navigation, they would still face the one adversary that no technology anywhere in the universe has ever defeated: entropy, the silent force dissolving everything ever built. What is the longest any complex machine built by humans has operated continuously without external maintenance? 6 barriers have now been examined in sequence. Distance measured in thousands of light years. Energy requirements that exceed the productive capacity of entire civilizations. Journey durations that outlast the civilizations that launched the missions. Radiation environments that erode materials and biological tissue without pause. Communication blackouts so complete that no meaningful support from home is possible across any practical time frame. And the near total invisibility of Earth from any useful distance. Each one of these barriers, taken alone, presents a challenge that no civilization in human history has ever come close to overcoming. Together they form an interlocking system with no weak point. There is a 7th barrier. It is quieter than the others. It does not announce itself with dramatic numbers or striking comparisons. It operates slowly, incrementally, and without any possibility of negotiation. It is entropy, and it is the only force in the known universe that has never lost. The second law of thermodynamics states that within any closed system, the total entropy, the measure of disorder, always increases over time. Order does not maintain itself. Concentrated energy disperses. Complex structures break down into simpler components. Organized systems drift toward equilibrium with their surroundings. This law applies without exception to every physical process that has ever occurred anywhere in the observable universe. It is not a tendency or a statistical preference. It is a direction built into the structure of time itself. For an interstellar spacecraft, this means one thing with absolute clarity. Every component aboard the ship is degrading from the moment of launch, not because of poor engineering, not because of inadequate materials, because the universe requires it. Radiation from the interstellar medium displaces atoms from semiconductor crystal lattices one by one, accumulating defects that gradually reduce the performance of every electronic system aboard. Thermal cycling, the expansion and contraction of materials as the ship moves through regions of slightly varying temperature, stresses every joint, every seal, every welded connection repeatedly across centuries. Metals develop fatigue fractures at stress points. Polymer seals harden and crack. Lubricants in any mechanical system slowly break down into compounds that no longer perform their function. The ship is not in a neutral environment that preserves it in stasis. It is in a slow-motion disassembly process that never pauses and never reverses. The most instructive real-world data point is Voyager 1, launched in 1977 with a planned mission duration of 5 years. Voyager 1 is now 47 years into its operational life and still transmitting. That achievement is genuinely remarkable. But the details of its current condition illuminate exactly what entropy does to machines over time. Multiple scientific instruments have been permanently shut down to conserve the dwindling power output of its radioisotope thermoelectric generators, which lose approximately 4 watts of output every year. NASA projects that all remaining scientific instruments will will cease functioning before 2030. The spacecraft is not maintaining itself. It is dying by degrees, system by system, year by year. And Voyager 1 carries no life support systems, no pressurized compartments, no temperature-controlled habitable spaces, no biological systems requiring precise atmospheric composition, no water recycling infrastructure, no food production, no medical equipment. It is an extraordinarily simple machine by the standards of anything that would need to sustain human life. And even this simple machine cannot maintain full functionality across a century without degradation that permanently removes capabilities. The mathematics of reliability engineering makes the long-term picture precise. A system with an annual failure probability of 0.001%, meaning 1 chance in 100,000 of catastrophic failure in any given year, has a probability of surviving 10,000 years intact of approximately 0.005%, functionally zero. To achieve even a 50% probability of surviving 10,000 years without a single critical failure, a system must have an annual failure probability lower than 1 in 144,000. No engineering discipline in human history has demonstrated reliability at this level for a single complex system, let alone for thousands of interdependent systems operating simultaneously in the most hostile environment the universe offers. When something breaks on an interstellar ship, there is no supply chain to draw from. Replacement components must be manufactured from materials carried aboard the vessel, but those materials are finite, and the machines used to manufacture replacements are themselves subject to the same degradation processes as everything else on the ship. The knowledge required to fabricate a specific component depends on specialists who may have died centuries earlier, leaving records that subsequent generations may or may not have successfully preserved and understood. Entropy cannot be defeated by better technology. A more advanced civilization builds more sophisticated machines, but sophisticated machines have more components, more interfaces, more potential failure points. Complexity does not reduce entropy's reach. It expands the surface area. Entropy has to work on. The direction of time is not a problem that the next generation of engineers will solve. It is the condition under which every engineer in the universe operates. Distance, energy, time, radiation, isolation, entropy, 6 walls, each one alone sufficient to stop. Together, they form a cage with no exit. But let me ask the final question, the one that almost nobody dares to ask. Even if all of this were wrong, even if a civilization somehow overcame every single barrier, would they actually want to come here? If billions of civilizations could exist in the galaxy, why have we heard nothing? Every barrier examined across the previous 13 parts leads to the same destination. Not a planet, not a star system. A question. A question so simple that a physicist once asked it over lunch, and the scientific community has never fully recovered from the asking. In 1950, Enrico Fermi was eating in the cafeteria at Los Alamos National Laboratory when a conversation about UFO reports and the possibility of interstellar travel prompted him to pause and ask something that nobody in the room could answer. The question was not complex. It was 4 words. Where is everybody? Fermi had done what physicists do instinctively. He had run the numbers in his head. The galaxy is roughly 10 billion years old. Stars have been forming for most of that history. Planets are common. If even a small fraction of those planets produced intelligent life, and if even a tiny fraction of those civilizations developed interstellar travel, the galaxy should by now be saturated with their presence. Signals, probes, colonies, artifacts, something. The numbers said the sky should be full of evidence. The sky was silent. That gap between what the numbers predicted and what observation confirmed became known as the Fermi paradox. 11 years later, in 1961, astronomer Frank Drake formalized the question into an equation. The Drake equation estimates the number of communicating civilizations currently active in the Milky Way by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually emerges, the fraction where intelligence develops, the fraction that develop detectable technology, and the average lifespan of such civilizations. Plug in optimistic but not unreasonable values for each factor, and the equation produces estimates ranging from dozens to thousands of active civilizations in the galaxy at any given moment. Thousands of civilizations in our galaxy right now. And yet since 1960, the search for extraterrestrial intelligence program has been listening. Radio telescopes of increasing sensitivity have scanned billions of frequency channels across hundreds of thousands of stars across more than 6 decades of continuous operation. The total result is one anomaly. On August 15, 1977, astronomer Jerry Amon, reviewing data from the Big Ear radio telescope at Ohio State University, circled a signal on a printout and wrote a single word beside it. Wow. The signal lasted 72 seconds, matched the expected profile of an extraterrestrial transmission, and originated from the direction of the constellation Sagittarius. It was never detected again. Every subsequent attempt to find it, using more powerful instruments pointed at the same region of sky, has returned nothing. The WOW signal remains unconfirmed, unexplained, and unrepeated. The Allen Telescope Array in Northern California, currently one of the primary instruments dedicated to SETI research, monitors millions of frequency channels simultaneously from hundreds of thousands of stellar targets. The silence it returns is not the silence of limited sensitivity. It is the silence of a sky that, by every measure available to the most sophisticated listening instruments humanity has built, contains no detectable deliberate signal from any technological civilization. Several explanations for this silence have been proposed and debated seriously within the scientific community. The Great Filter hypothesis suggests that somewhere along the path from simple chemistry to spacefaring civilization, there exists a barrier so formidable that almost nothing gets through it. If the filter lies behind us, it means the emergence of complex life is extraordinarily rare, and we are among the vanishingly few civilizations to have made it this far. If the filter lies ahead, it means advanced civilizations routinely destroy themselves before achieving any lasting presence, and our own future contains the same trap. The zoo hypothesis proposes that other civilizations are aware of us and have collectively agreed not to make contact, observing us the way researchers observe a wildlife preserve. The dark forest hypothesis, developed as a theoretical framework by physicist Liu Cixin, proposes that the silence is a survival strategy, that any civilization that reveals its location to the universe invites destruction from others, and that the rational response to the cosmos is to hide. Each of these explanations carries its own unsettling implications. But after everything examined across this analysis, a simpler explanation sits quietly at the center of the picture, requiring no conspiracy, no collective decision, no cosmic predator. Nobody comes because nobody can. The physics that prevents humanity from reaching the stars applies with identical force to every other civilization in the galaxy. The Great Filter is not a biological bottleneck or a self-destruction tendency. It is geometry. It is energy. It is time. The walls are not built from the failures of civilization. They are built from the structure of space-time itself, and they surround every mind that has ever looked upward from the surface of any world anywhere in the observable universe. The James Webb Space Telescope provided a genuinely remarkable data point in this context. In 2023, analysis of JWST observations of the exoplanet K218b, a world approximately 8.6 times Earth's mass orbiting a cool red dwarf star 120 light-years from Earth, detected the presence of carbon dioxide and methane in its atmosphere. Some researchers noted that the simultaneous presence of these molecules in certain proportions could be consistent with biological processes. Though the interpretation remains actively debated and no consensus on biological origin has been reached, the finding demonstrated that JWST can detect atmospheric chemistry at interstellar distances. It also confirmed that 120 light-years away, the best telescope humanity has ever built can identify atmospheric molecules, but cannot resolve a civilization, cannot detect a city, cannot hear a signal. The silence does not prove they are absent. It confirms that the universe built walls around every one of them, the same walls it built around us. Every civilization that exists right now, if any do, is standing behind those walls, looking outward into the same silence we observe, asking the same question Fermi asked over lunch in 1950. The silence is universal. The isolation is structural. The question echoes across the galaxy with no answer because the galaxy was never designed to carry answers across the distances that separate the ones asking. But what if this silence is not a wall? What if it is an invitation? We started with a lie. The night sky tells every human being who has ever looked up. We followed that lie through 14 layers of physical reality, each one more unforgiving than the last. Distance that breaks every analogy. Energy costs that no civilization can escape. Time that outlasts everything built to cross it. Radiation that erodes without pause. Silence that no signal can bridge in any meaningful time frame. Entropy that takes apart everything. Always, without exception. Every wall we examined was not a dead end. It was a deeper question wearing the shape of an obstacle. Here is where we actually stand. We know enough physics to see the prison clearly. We do not know nearly enough to be certain nothing exists beyond its bars. The same science that maps the barriers also keeps finding planets, keeps detecting complex chemistry in distant atmospheres, keeps expanding the definition of where life might persist. We stand at the outer edge of our own understanding, which is exactly the most dangerous and most honest place to stand. If every civilization is sealed inside its own bubble of isolation, then each one is a candle burning in a vast darkness, unaware that millions of other candles may be burning somewhere in that same darkness, each one asking the same question, each one surrounded by the same silence, each one looking outward and finding no answer. The question stopped being, "Where is everybody?" a long time ago. The real question is what we do with our candle while it burns. The universe is holding too many secrets, and that darkness is not something to fear. It is something calling to us.